All right, so now we're going to talk about forces and Newton's laws. So, what are forces? Well, it's best to describe forces by some of their properties, right? So, forces are something that act on an object, they're a push or a pull. Forces don't have to be in contact with something. So, a great example of that is gravitational force. Gravitational force produces a pull on objects towards each other, but these objects don't have to be in contact. So there are contact forces, like a physical push or a physical pull, normal force, but there are also non-contact forces like gravitational force and electrostatic force. Forces also require an agent, meaning that there has to be some sort of identifiable cause. And also, forces are vectors. They have magnitude and they have directionality to them. So, before we dive totally into forces, let's think about just motion, right? So, if you're in a car and you're going 60 miles per hour and the driver slams on the brakes really fast, what happens? Well, originally, right, you were just traveling in the car. If they slam on the brake, you are going to lean forward. Why does this happen? Well, this happens because of Newton's first law. Newton's first law tells us that an object in motion is going to stay in motion, an object at rest is going to stay at rest, unless there is some non-zero force acting upon it, right? So this gives us the idea of inertia, right? So Newton's first law is also sometimes called the law of inertia, and inertia just means resistance to change in velocity, right? So what is a change in velocity? A change in velocity is acceleration. And this doesn't have to just be a change in the magnitude of velocity, right, or the speed of the object. This also can be a change in direction. So inertia just means that objects have a resistance to change in the magnitude or direction of their velocity unless acted on by a force, right? So it's important to also note that this doesn't mean that there is a resistance to continuation of motion. It just means there is a resistance to a change in motion. So Newton's second law is probably the one that we are going to interact with the most in this class, and this is just the definition of force, right? So the force acting upon an object is proportional to the acceleration of the object. So F is equal to ma. Force is equal to mass times acceleration. And then you have Newton's third law, which is the law of equal and opposite forces. So the force acting on object 1 from object 2 is going to be equal in magnitude and opposite in direction from the force acting on object 2 from object 1. So this is the idea of like interaction pairs. So every force is going to be part of an interaction between two objects, and each of those objects exerts a force on the other. So we can imagine, how do I want to draw this? This is a chair, and I am sitting, or you are sitting in this chair, right? You are acting on the chair with the force of gravity, right? And the chair is acting on you with a normal force, right? So there's this balance between you and the other object or two objects acting upon each other. One thing I also want to point out that is really important is this force of 1 on 2 is equal and opposite to the force of 2 on 1. This is referring to two different objects, two different objects. So if there are multiple forces acting on one object, we don't have to have this equal magnitude, opposite, and direction law. This is just thinking about two different objects. So a great example of that is going to be Newton's laws of gravitation, right? So every particle in the universe attracts every other particle in the universe. So the most common way that we think about this is we think about like the Earth, and we think about the moon, and we think, okay, well, the moon is pulling on the Earth, and the Earth is pulling on the moon, right? So we have this law of gravitation. So we have the mass of object 1, this could be the moon, and the mass of object 2, this could be the Earth. R is our distance between them. And then we have this G. This G is our universal law of gravitation. So what this gives us is the force acting between these two objects. So gravitational field strength, right, is going to be how we describe this pull that you would feel at any point around some mass. So I really want to drive home the idea that this doesn't have to just apply to planets, right? This applies to any objects that have a mass. They apply a pull between the two objects. This law of gravitation is not restricted to large massive objects. It happens between anything that has a mass. Now, the magnitude of this gravitational field strength, obviously between like one person and another person, is going to be very, very small. We're not going to feel it. It may not have an impact on any calculations that are done, but it does exist. So, what is gravitational field strength? Well, for an object that is near Earth's surface, we can assume that the radius of the Earth is 6.37 times 10 to the 6 meters, and the mass of the Earth is 5.97 times 10 to the 24 kilograms. So the weight, or the force due to gravity, of this object is equal to the gravitational constant times the mass of object 1, mass of object 2, divided by the radius between them. So let's assume that there is an object, and this object, we're just going to call it M1, is sitting on the Earth. So mass 2 is going to be the mass of the Earth, and the radius between that object and the Earth is going to just be the radius of the Earth. So I'm going to pull this M1 out, and I'll just replace it as M, and then I have this value, right, which in our situation, when objects are near Earth's surface, these are all going to be constant values. So the weight, or the force due to gravity, is equal to the mass of my object times whatever this constant is. And whenever we calculate it, this constant is g. So if you remember, we had a statement that the acceleration due to gravity is equal to negative g, which is equal to negative 9.81. This g is 9.81. That's how we get this g value. So now we have our first force, right? Sometimes you'll see it written as weight. Sometimes you'll see it written as the force due to gravity. Either one of those is correct. Depending on the textbook, kind of depends on which one is used. And so this weight, right, whenever we turn into the vector force, is negative mg. And this is because, right, the force of gravity is a force, so negative mg is equal to mass times acceleration. Acceleration equals negative g, or negative 9.81 meters per second squared. The next force is going to be a kind of response force. It's a contact force, and this is going to be called our normal force. So if we have this book sitting on a table, this book has a force of gravity that's pulling it down, but there has to be some force coming from the surface of this table that stops this object from moving down further. And that force is going to be the normal force, or the response force. Whenever an object is in contact with another object, there's going to be a normal force between them. So this normal force is always going to be perpendicular to the contact surface. And this is really important because in our most basic example, right, a block sitting on a table, we have the force of gravity downwards, we have this normal force pointing upwards, and people always assume that the force of gravity is always going to be opposite the normal force. An example where that's not the case is a block on an inclined surface, right? So on an inclined surface, the force of gravity is still going to be pointing down directly towards the center of the Earth, but my normal force is normal to the surface of this inclined plane. So now my normal force is coming off at an angle. So our normal force is always going to be perpendicular to the surface that this object is sitting on. And this normal force just ensures that the object stays on the surface without penetrating the surface, right? It's this response to the weight of the object. The next basic force that we can think about is a tension force, right? Kind of like a pull response force. And we have tension forces whenever we have a rope, right? So we assume that this rope is going to be an idealized rope. So if I have people playing tug of war and each of them is pulling on the rope, each one is going to be applying tension, that's a T, to the other. And whenever we think about ropes in a general physics class, we make a couple assumptions. The first one is that this rope doesn't stretch. Why? Because incorporating stretching is going to be mathematically complex, and we're not at that point yet. And two, the error value is not going to be great enough to really produce a significant issue in the problems that we are doing in this class. So because this rope doesn't stretch, we also assume that the force transmits throughout the entire rope undiminished from end to end, meaning that whatever force this person 1 applies to the rope, person 2 is going to feel that exact same force. So it goes all the way through the rope without diminishing or getting smaller. The next force is going to be the friction force. And the friction force is kind of like a resistive force. It's resistant to motion. It always points in the opposite direction of the relative motion of the object. So there are a couple of different types of friction forces we're going to talk about too. So friction forces do not arise between objects unless the objects have some force that's pushing them together. Makes sense, right? If you take your hands and you rub your hands together really fast, right, there's friction between these, right? They're touching each other. I am applying a force to push my hands together. Now, if I take my hands and they're separated by like an inch and I move them back and forth, there's no friction that's occurring because the objects aren't touching each other. So objects have to touch each other in order for there to be a friction force. So what is that force that's pushing them together? Well, if we have an object, right, we have two objects. Let's say we have a carpeted ground and we have your foot that kind of looks like a duck foot, but go with it, right? And you have the weight of your foot, and then you also have this normal force. So if we actually zoom in, what we would see is a rough atomic surface on the bottom of your foot, and then a rough atomic surface of the carpet. So there are two types of friction that we're going to think about in this class, right? And it's going to be static friction and kinetic friction. Static friction happens whenever things are stationary, right? So we can think about an object resisting initial motion. Kinetic friction happens whenever objects are already in motion, right? So this is the thing that actually slows an object down whenever it is already in motion. And these have slightly different equations, but they're very similar to each other, right? So with kinetic friction, we have the force of kinetic friction is equal to mu sub k. So this is going to be the coefficient of kinetic friction. This is the Greek letter mu, and the sub k just tells us that this is the kinetic friction. And then it's going to be multiplied by the normal force. Why is it multiplied by the normal force? Because the normal force is going to dictate, right, the magnitude of the magnitude of the force that is getting these two objects in contact with each other. So if we have a large normal force, we're going to have a large force due to friction, and if we have a very small normal force, we will have a very small relative frictional force scaled by the coefficient of kinetic friction. So kinetic friction occurs when an object is moving. When an object is in contact with a surface and it slides against that surface, you get kinetic friction. And this force of kinetic friction is equal to the coefficient of kinetic friction, mu sub k, times my normal force. Now, what about static friction? Static friction is interesting because it's not equal, it is less than or equal to the coefficient of static friction times the normal force. So what does that mean? That means that our force of static friction is going to be increasing up until it is equal to the coefficient of static friction times the normal force, then our object is going to start moving. So static friction occurs when an object is stationary, and the static friction is less than or equal to the coefficient of static friction times the normal force. So the coefficient of friction just represents the amount of friction that occurs between two different surfaces. So I think it's really important to note that an object by itself does not have a coefficient of static friction. This is not an intrinsic property of an object. It is the interaction of two surfaces that determines the coefficient of static friction. So rubbing my hand or my shoe against concrete is going to have a different coefficient of static friction, or I guess kinetic friction if I'm moving it, than rubbing my shoe against ice or rubbing my shoe against carpet, right? My shoe is a constant in all of these, but my coefficient of friction is going to be different because it's dictated by the interaction of two objects. So how does this occur? Well, friction is determined by, right, two objects interacting with each other. In this case, we have a physics textbook and we have a chemistry textbook. So friction actually arises due to the rough atomic surface of objects, right? So, oh, this comes with sound. So my chemistry textbook has a fairly rough atomic surface, right? We have all these little atoms, and at the atomic level, nothing is perfectly smooth. There's always going to be like this jagged layer that occurs. So whenever these objects rub against each other, it causes friction. Why? Because we have these little outcroppings of atoms that are touching the atoms of the other object. Now, what's really interesting is that friction is also a dissipative force, meaning that it dissipates energy. We'll talk about this whenever we get into the conservation of energy, but whenever we have two objects and we rub them against each other, like our hands, right, we rub them together fast enough, it produces heat, right? And we can see that on our thermometer on the right-hand side. So how do we move from static to kinetic friction? So let's think about a situation. Let's say that we have a block on a movable incline, and I can continually increase the incline of this surface. At some point, I'm going to transition from this block being stationary to this block in motion. What happens? Well, our force of static friction is less than or equal to our coefficient of static friction times my normal force. So as this incline changes, my normal force is also going to be changing. My force of static friction is going to increase up until it hits this equals to. Once it hits this equals to, I'm going to transition from static to kinetic friction. So there is going to be a transition, and that is going to be the moment that this object starts to move. So there's also other resistive forces like drag forces due to air resistance, but we're not going to cover that. So the list of forces that we need to think about whenever we start solving problems is going to be the force due to gravity, or the weight of the object, the normal force, the tension force, and these static and kinetic friction forces. So what happens if we have an object that has multiple forces acting on it, right? So let's say we have a block and we have two people pulling at the block. We have two different tension forces. How do we determine what direction this object is going to move in? Well, we need to think about the net force on the object, right? So when one or more forces act on an object, the motion of this object is going to be determined by the net force, or the total force. So the net force is just going to be a sum of all of the forces acting on the object. And recall that a force is a vector. So all of these summations have x and y components in them. In this situation that I have drawn, obviously we only have an x direction, but if I have a block on an inclined plane, I will have x and y directionality here. So our summations, we have to break everything down into x and y, just like we did with 2D kinematics. But what about a situation where I still have this static friction, right? Static, stationary. We will have equilibrium, right? So when the summation of forces acting on the object is equal to 0. One common misconception that I see is that if an object is in equilibrium, it has to be stationary. And that's not true, right? That's because our force is equal to mass times acceleration. Acceleration is a change in velocity over a change in time. If a is equal to 0, that just tells us that my change in velocity is equal to 0. I don't have any acceleration. That doesn't tell me that I don't have any velocity, right? So there are two different cases for equilibrium. There is static equilibrium, when there is no motion, my object has no velocity, but there's also dynamic equilibrium, right? When I have some velocity, but I do not have an acceleration, right? There's no change in my velocity. So what is the problem solving method for forces? The first thing you want to do, draw a problem and do a free body diagram or a force diagram. And we'll talk about that later, right? Identify all the forces. Then we'll need to create an equation of forces for the x and the y directions and replace force variables with specific variables, check your directionality, and then solve the algebra.